All right, noisy neighbor detection with eBPF. If you haven't heard me rant about eBPF before, extended Berkeley packet filtering is a way you can run user space code inside of the kernel. That is useful from both a performance standpoint, where you don't have to copy data in and out of the kernel to make use of it. So you can do things normally would have caused a pretty big latency penalty, like inspecting every single packet or running a callback when you read or write to a file. You can do those things much faster inside of the kernel, but you have to stick to a couple of specific rules. Okay, so the compute and performance engineering teams at Netflix regularly investigate performance issues in our multi-tenant environment. The first step is determining whether the problem originates from the application or the infrastructure. One issue that often complicates this process is the, quote, noisy neighbor problem. On Titus, that's quite the name, Titus, our multi-tenant compute platform, a noisy neighbor refers to a container or system service that heavily utilizes the service's resources, causing performance degradation in adjacent containers. We usually focus on CPU utilization because that's our workload's most frequent source of noisy neighbor issues. Okay, so they're packing a bunch of packing a bunch of containers on a VM or a host, and they're probably clearly overpacking. And I think the idea is that every CPU cycle will do useful work. Detecting the effects of noisy neighbors is complex. Traditional performance analysis tools such as perf, shout out perf, we love perf on this stream, can introduce significant overhead, risking further performance degradation. True, that is the challenge. Perf event open is an expensive system call to track. You put counters on every single syscalls, and those get really spendy. Additionally, these tools are normally deployed after the fact, which is too late for effective investigation. Also true. Another challenge is that debugging noisy neighbor issues requires significant low-level expertise and specialized tooling. Also true. In this blog post, we'll reveal how we leveraged eBPF to achieve continuous low-overhead instrumentation of the Linux scheduler, effectively enabling self-service monitoring of noisy neighbor issues. And then you can learn about the kernel in this post. Okay. Very neat. They're instrumenting the run queue latency for each container, which measures the time processes spend in the schedule queue before being dispatched to the CPU. Extended waiting in this queue is a telltale sign of performance issues, especially when the containers are not utilizing their total CPU allocation. So each container has a certain amount of CPU it can use in a given time period. Maybe it's a minute, maybe it can use whatever, 10 million cycles. And if you're under that number, but you're waiting for the schedule to run you a lot, that means that you have a noisy neighbor, right? Something else is stealing those cycles and you're unable to execute. Continuous instrumentation is critical to catching such matters as they emerge, and eBPF, which hooks into the Linux scheduler with minimal overhead, enabled us to run and monitor run queue latency efficiently. To emit a run queue latency metric, we leverage 3 eBPF hooks: schedule wake up new, and schedule switch. This is a sick diagram. I love this diagram. So your run queue is going to hold all of the waiting processes to be executed. I think they're in time order. So this is it is a stack, and this is the next instruction to run. Previous, next pointer. Oh no, sorry, it grows upward. Okay, still a stack, different direction. Okay, so schedule wake up and schedule wake up new hooks are invoked when a process changes from sleeping to runnable. So when your process is done waiting for IO, it will invoke that hook, schedule wake up and schedule wake up new, and they identify that the process is ready to run and is waiting for CPU time. During this event, generate a timestamp and store it in a hash map using the process ID as the key. T2 is when the task came out of queue. So T1 is when it went into queue, and then you wait. T2 right here, boom, it gets executed, and then it can go back in if it has another instruction to run. And it's tagged by who preempted, which is important because if you get bumped, you want to know who did it. And it's calculating the rate of preempted tasks per second. Okay, makes sense. Let's read some C code. So they have a hash map, and then the max number of entries, and they have a key size U32s, and then a value size U64. Those values are timestamps, right? And the key is the process ID. So they're grabbing this schedule wake up, and then they write the task ID, and then the timestamp here, and then they update the map and return 0. So that gets run every time. It's hooked into this method. So every time schedule wake up is called, it's going to actually run this method. It's going to grab the process ID and write down the time it was scheduled to wake up. And that's when it goes into the bottom of the queue. Conversely, the schedule switch hook is triggered when the CPU switches between processes. This hook provides pointers to the process currently utilizing the CPU and the process about to take over. So now you have both. We use the upcoming task process ID to fetch the timestamp from the eBPF map. This tells us when the process entered the queue we had previously stored, and then we calculate the run queue latency by subtracting the timestamps. Makes perfect sense. So you know what you're going to execute next. Inside that hash map is a pointer for where it started. You can look it up, you can do the subtraction, and then you can emit that. One of the advantages of eBPF is its ability to provide pointers to the actual kernel data structures representing processes or threads, also known as tasks in the kernel terminology. I'm not a kernel expert. Let's learn together. This feature enables access to a wealth of information stored about a process. We require the process's C group ID to associate it with the container for our specific use case. However, the C group information is in the process struct and safeguarded by a read copy update lock. To safely access the RC provided protected information, we leverage the K-funcs in eBPF. So exposed kernel functions that eBPF can call. If you haven't written an eBPF program or you haven't read them, they have very limited instructions for what they can actually call. It's part of the security implementation for eBPF programs. They also, as far as I know, you can't do things like loop or branch unconditionally because they need to run deterministically. You have to call these specific methods, in this case K-funcs, to look up this data. This function can lock and unlock the RCU read side critical section just so you can read that data, ensuring it remains safe and efficient. So this is how they look up the task group ID. They call that read lock, they call task.cgroups, and then they go off and grab that ID for that kernel task. Then they unlock it and return the ID. When the data is ready, we have to package it and send it to user space. Okay, this is the other thing that's kind of important. If you've learned or read about IOU ring, you know why escaping kernel space to user space is such a performance sensitive part of the code base. They're using a ring buffer, which is exactly what IOU ring does too. And they're doing that because it's efficient, high-performing, user-friendly. They can handle variable length records, and then it can allow data reading without extra memory copying or syscalls. That's key. IOU ring does the exact same thing. So they allocate memory in the kernel, inside of their kernel process, and then when the user process starts up, it memory maps user space memory into that kernel space. So when you read or write from memory in the kernel space process, it's in the kernel. When the user space program runs, it can read straight out of the kernel itself instead of actually, even though it looks like it's reading from its own memory space, it's reading it from the kernel space. That's what mmap is doing for you. That avoids an actual memory copy and a syscall, which is why you can keep this up at line speed. And the whole point is like, you're trying to keep up with the rest of this program that is running at this crazy speed, but you're trying to do it in a way where you don't use too much resources, but you still get the data you need. And that is why eBPF is so useful here. The sheer number of data points cause the user space program to use too much CPU. Very common in performance programming. So we had to implement a rate limiter in eBPF to sample the data. Makes perfect sense. So this is going to be their rate limiter. So they do a per C group ID per CPU rate limiting to balance observability with performance overhead. And then they decide whether or not to drop that point. So if they exceed the rate limit, where now minus lab timestamp is less than the rate limit in nanoseconds, and they're getting these in nanos, so it's cooking, then they drop the event. And then they insert it into the ring buffer, and then the ring buffer can be picked up by the user space program. And that's just the insertion call for that ring buffer. They update that element right here. Oh, sorry, they submit it to the ring buffer, and then they update it, and they say, okay, the last event timestamp was like now. Yeah, I assume. Okay. Our user space application, developed in Go, processes events from the ring buffer and emits metrics to our metrics backend, Atlas. Each event includes a run queue latency sample with a cgroup ID, which we associate with containers running on the host. We categorize it as a system service if no such association is found. When a cgroup ID is associated with a container, we emit percentile Atlas metrics for the container. We also increment the counter metrics to monitor preemptions occurring for the container's process. So that's what they know. Now they know how long it's spent in that run queue waiting for its instruction to get called, and if it's preempted, and if so, by whom. And then I also think it knows the current execution and then the next execution, so you can see who's blocking you all the time. The run queue latency for a server running a single container with ample CPU capacity, the 99th percentile is 83 microseconds, serving as our baseline. Although there's some spikes reaching 400, it's within accepted parameters. Okay, that's fine. Okay, now they scheduled on the container, which fully utilized CPUs on the host, causing a significant 131 milliseconds, so it's 131,000 microseconds in container one's P99 run queue latency. This spike would be noticeable in the user space application if it were serving HTTP traffic. This is like a packing story too, right? Like a bin packing story. If they had a super noisy container 2, which is just going to pin every CPU, maybe it is a HTTP service itself, but if they were running another HTTP service that's also latency sensitive, you would notice it because all of a sudden, I mean, it added 131 milliseconds to a P99. Like that's substantial. That's effectively like a cold start on every request. That's painful. If the user space app owners reported an unexplained latency spike, we could quickly identify the noisy neighbor issue through the run queue metrics. Super handy. Optimizing the code. We developed an open source eBPF process monitoring tool called BPF Top to measure the overhead of eBPF code in the kernel hot path. Our profiling with BPF Top showed that the instrumentation adds less than 600 nanoseconds to each schedule hook. That's pretty solid. We conducted a performance analysis on a Java service running in a container, and the instrumentation did not introduce significant overhead. That's always good to feel. The performance variance with the run queue profiling code active versus inactive was not measurable in milliseconds. All right. Oh, during the research, they found an opportunity to improve the calculation for how eBPF statistics are measured in the kernel, and they submitted a patch. What did they do? Improve. Oh, okay. So they record 2 timestamps from the clock, and then they record the duration, and then instead of calculating it down here, they just already have scheduled it. Okay, that's helpful. Making this change to the patch facilitates more precise optimization. Yeah, exactly, because they're recording done as actually when the code finished, instead of how long it took to update the graph. So pretty clever, pretty smart. I've had to make these changes in our metrics as well, a couple different places where we were inadvertently measuring like our own changes on top of like, in this case, what the customer is doing. So, there's some function here that it's going to run, and then they wanted to end the duration here, and that's exactly what they wanted to do. Shed clock, I assume, just gets the current time. If that's not, someone jump into the comments and correct me. Conclusion, our findings highlight the value of low overhead continuous instrumentation of the Linux kernel with eBPF. We've integrated these metrics into customer dashboards, enabling actionable insights and guiding multi-tenancy performance discussions. This is good. They figured out how to make their packing and their scheduling more cost efficient, which means they can run more workloads at the same time. So pretty sweet. I like this. Love to see this. And I want to see other eBPF related performance things. So if you have any, send them to me. All right. I'll see you in the next one. Thanks.